Hi, so we're going to work through the exercises for the nucleation. So we're going to start off by thinking about the volume per particle in the liquid droplet, and we're going to use that to calculate the surface area of our cluster. Okay, so let's have a go at that. So, we're going to say that VL is our volume per particle in the liquid droplet. Okay, and so if we write down the volume of our whole cluster, we're going to say the volume of our cluster of size I is 4/3 pi r cubed, where r is obviously the radius of our cluster, which is equal to I, the number of particles in the cluster, times the volume per particle. So now we can rearrange this to write it in terms of the radius. So we're just rearranging this here. So r is, so we've got 3/4 IVL, and then we're going to divide by pi, and then that's going to be to the power of 1/3. Okay, but the surface area of our cluster of size I, so AI is of course equal to 4 pi r squared. And we've derived our expression for r up here, so we're going to substitute that in here. So this is going to be equal to 4 pi IVL times 3 and of course all of that is squared, so this is IVL times 3/4 pi to the 2/3. Okay, so now you can see where these weird 2/3 powers come from. So let's take the constants out. So taking the constants outside, so we've got 3/4 pi. This is to the 2/3, and we still got left IVL to the 2/3. Okay, so now let's have a look at this thing here. So this is 4 pi, so that's to the 3rd. Oh yes, because we've got the 4 pi on the bottom, so times by 3 to the 2/3 times by IVL to 2/3. So that is equal to 4 pi times 3 because it's squared, but now it's all to the 3rd VL to 2/3, which is equal to 3/4 12 times 3 is 36 pi to the 3rd IVL to the 2/3. And that's the first part done. So now we have our surface area of our cluster in terms of the number of particles and the volume per particle in the liquid phase. We can write down the free energy associated with the surface term. So we can write that as, let's just say delta G, let's just call that S for the surface term, and that's going to be our surface tension times by what we've just derived, so 36 pi to the 3rd VL to the 2/3 I to the 2/3, because this is the surface area of our cluster, and to get the free energy associated with that, we multiply by the surface tension. So this is the unfavourable surface term, and then we've got the favourable volume term, so delta GV is equal to minus I kT log of the supersaturation. That's our volume term. So our actual free energy barrier for our cluster, so delta G is delta G for the surface plus delta G for the volume. So we add together the unfavourable surface term and the favourable volume term, and we get for our barrier sigma 36 pi to the 3rd VL to the 2/3 I to the 2/3 minus I kT log of the supersaturation. So that is our free energy barrier to nucleation as a function of the size of the cluster. Okay, now we want to find the size of the critical cluster. So we want to find where this free energy barrier has a maximum, because that's what defines the free energy of the critical cluster. So what we're going to do is we are going to do d by di of delta G. So we're going to differentiate our free energy area and set this to 0, because this is going to tell us the maximum, which is where our critical cluster is. So this is 4I star, our critical cluster. Okay, so let's have a go at this differentiation. Okay, so just doing this differentiation, we've got d by di of sigma 36 pi to the 3rd VL to the 2/3, all boring constants, I to the 2/3 minus I kt ln s. Okay, so this is going to give us pi to the 3rd times by sigma times by VL to the 2/3. Now this I, we've got now times by, this is what we're differentiating, 2/3I to the minus a 3rd minus, and we just get rid of this I here because we're differentiating, kt ln s, and that is all equal to 0 for our critical cluster. So this here, this I here, because we differentiated, is actually I star. So let's put that in there, give it a little star to show that it's special. Okay, so now we've got 36 pi to the 3rd sigma VL to 2/3 times 2/3I star to minus a 3rd 1/3, and that is equal to kt ln s. I've just taken this over to the other side. Okay, so basically what we want to do is we want to rearrange this and write this in terms of our critical cluster I star. So I star to the minus a 3rd is equal to, right, okay, so we're just taking all of these things over to the other side. So we're going to do 3 kt ln s divided by this 2, and then we've got 36 pi to the 3rd times by sigma times by VL, okay, to the 2/3, okay. And we can now write I star is equal to, so now what we're going to do is we're going to flip this upside down because it's to the minus a 3rd, and cube everything. So we've got 2 cubed, this 36 pi here was to the 3rd, so now it's just 36 pi. We've now got sigma cubed, and we've now got VL was to the 2/3, so now it's just squared, so VL squared divided by, and we've got 3 cubed, which is 27, and then all of this in here is cubed, so we'll keep it all together, kt ln s all cubed. And this is our expression for our critical cluster.